The Moon is Earth's only natural satellite and has been a major point of interest as the closest neighbor in the solar system. Its surface has captivated human curiosity and imagination for thousands of years. This mysterious world, the first to be walked on and explored by humans, has become better understood thanks to geological processes in space exploration. The surface of the Moon is highly diverse, consisting of many regions with distinct characteristics. It features large craters, mountains, plains, volcanic structures, and deep valleys. A significant portion of the Moon's surface is covered with craters caused by meteor impacts. These craters vary in size and depth, with one of the largest being the South Pole Aitken Basin near the Moon's south pole, which is also the deepest point on the Moon. The Moon's surface also includes many mountains. One of the tallest is Mons Huygens, which stands at approximately 5,500 meters high. Some of these lunar mountains have volcanic origins. The Moon's volcanic activity was a result of its interior cooling down due to radioactive decay. This activity led to basaltic lava flowing to the surface, forming wide plains. One of the most famous of these plains is Mare Imbrium, a vast basalt lava plain known as the Sea of Rains. Valleys on the Moon's surface are another notable feature. These valleys are often associated with impact craters and can be both long and deep. One of the longest is Remus Ursalis, located in the southern hemisphere, stretching around 300 kilometers. Another significant feature of the Moon's surface is the layer of fine dust and sand known as regolith. This regolith is made up of particles formed from meteor impacts and covers the Moon's surface, influencing its color and texture. Because the Moon lacks a thick atmosphere, its surface is exposed directly to the vacuum of space. As a result, the surface experiences extreme temperatures. On the side facing the Sun, temperatures can rise to about 130 degrees Celsius, while on the side away from the Sun, temperatures can drop to as low as -180 degrees Celsius. The formation and evolution of the Moon's surface is a major area of research for scientists. While the craters on the surface are primarily the result of meteor impacts, volcanic activity and crustal fractures have also played a key role in shaping the terrain. Additionally, the Moon's internal structure and thermal activity contribute to the formation of surface features. Discoveries made on the Moon's surface have provided valuable insights for humanity. Apollo astronauts who visited the Moon collected soil and rock samples and brought them back to Earth. These samples have been crucial in understanding the Moon's geological structure, internal composition, and history. Furthermore, spacecraft and satellites sent to the Moon have provided detailed maps and images of its surface. There are future plans for a more detailed examination of the Moon's surface. New lunar missions aim to gather more information about the Moon's geological structure, resource potential, and its possibility as a base for future space exploration. The regions on the Moon referred to as seas are actually called Maria, which is Latin for sea. However, these lunar seas are not like the water-filled seas on Earth. On the Moon, the seas are large basalt lava plains. The lunar seas are areas where basaltic lava flows once filled the surface. These lava flows were caused by volcanic eruptions in the Moon's past, spreading across the surface. The seas have a darker color and a smoother surface texture. Let's explore some of these lunar seas. Mare Tranquillitatis, one of the largest seas on the visible side of the Moon. It is famously known as the landing site of Apollo 11, where Neil Armstrong and Buzz Aldrin first walked on the Moon. Mare Serenitatis, another large sea on the Moon's visible side. It was visited by Eugene Cernan and Harrison Schmitt during the Apollo 17 mission. Mare Imbrium, one of the largest seas on the Moon, containing many craters. This sea is also located on the visible side of the Moon. Mare Nectaris, a sea located on the Moon's southern surface. The craters within this sea are well preserved and clearly visible. Mare Crisium, a sea situated on the eastern side of the Moon. It is surrounded by mountains that encircle its plains. The lunar seas provide valuable information about the Moon's geological history and volcanic activity. During space missions to explore the Moon, soil and rock samples have been collected from these seas. These samples have enhanced our understanding of the Moon's formation and evolution. Now, let's explore the mountains on the Moon. The mountains on the Moon are elevations formed through various volcanic and impact-related processes. While they may resemble mountains on Earth, their formation and characteristics differ significantly. Here are some of the notable mountains on the Moon. Montes Alpes. This mountain range is located in the northwest region of the Moon. It is named after the Alps on Earth and is known for its steep slopes and prominent peaks. Montes Caucasus, situated on the eastern side of the Moon, this long and winding mountain range is named after the Caucasus Mountains on Earth. Montes Caucasus is often found surrounding large craters. Montes Apenninus. This large mountain range is located in the southeastern region of the Moon. It lies near the Hadley crater, which was visited during the Apollo 15 mission. Montes Apenninus contains numerous mountain peaks and deep valleys. Montes Taurus, positioned on the western side of the Moon, this mountain range is named after the Taurus Mountains on Earth. Montes Taurus consists of several peaks and is located near various craters. Mons Huygens, a standalone mountain located on the Moon's southern surface, Mons Huygens rises to about 5,500 meters. It is one of the tallest mountains on the Moon and is volcanic in origin. The mountains on the Moon provide important clues about its geological history and volcanic activity. These mountains have been studied in detail during space missions, offering valuable insights into the Moon's formation and evolution. The craters on the Moon are depressions formed by meteor impacts. These craters provide significant information about the Moon's geological history and the general evolution of the solar system. The Moon contains many large craters, which are typically wide and deep depressions. Some of the largest craters on the Moon include the Bailey crater, located near the Moon's south pole with a diameter of about 303 kilometers, the Clavius crater on the southern surface of the Moon with a diameter of around 225 kilometers, and the Copernicus crater, a prominent crater on the visible side of the Moon with a diameter of approximately 93 kilometers. The Moon's surface is also filled with numerous small craters, which vary in diameter from a few meters to several kilometers. These small craters are the result of smaller meteor impacts and are usually distributed irregularly across the lunar surface. In the large flat plains on the Moon, known as Maria, there are craters ranging from a few hundred meters to several hundred kilometers in diameter. These mare craters generally have flat and smooth surfaces. Crater chains can be observed in areas where basalt lava flows have occurred on the Moon. These chains are formed during the emergence of basalt lava on the surface, where many small craters line up in a sequential pattern. The age of the Moon's craters varies depending on the frequency of meteor impacts. Newer craters generally have more distinct and sharp edges, while over time, erosion and other geological processes may alter their appearance. The discovery and mapping of craters on the Moon's surface have helped humans better understand the Moon. The first detailed crater maps were created by astronauts during the Apollo missions. During these missions, astronauts studied the craters to understand their origins, geological features, and formation processes. Some craters on the Moon are much larger than normal craters and are referred to as supercraters. These supercraters are notable for their vast size and depth. For example, one of the largest craters on the Moon, the South Pole Aitken Basin, has a diameter of about 2,500 kilometers and is located near the Moon's south pole. The study of craters on the Moon has prompted various scientific research on topics such as the effects of meteor impacts, impact kinetics, the origin of impactors, and the geological history of the Moon. The formation and distribution of craters help us understand the role of meteor impacts in the Moon's geological evolution. Many of the Moon's craters are named in honor of astronomers and scientists. For example, the Copernicus crater is named after the famous Polish astronomer Nicholas Copernicus. The names given to the craters on the Moon reflect the importance of scientific discoveries and space exploration. The craters on the Moon differ from those on Earth and provide significant insights into the Moon's geological structure, formation, and evolution. Future explorations and space missions will likely lead to the discovery of more craters on the Moon's surface, deepening our understanding of its development. The regolith layer on the Moon is a thin mixture of soil, dust, and rocks that covers the surface. The regolith layer offers crucial information about the Moon's geological past and the broader evolution of the solar system. The formation and composition of the Moon's regolith result from various geological processes. Meteor impacts transfer energy to the Moon's surface, breaking rocks apart and turning them into dust. These impacts scatter the rocks across the surface, contributing to the formation of the regolith layer. Additionally, the cooling and fragmentation of lava ejected during volcanic activity play a role in creating this layer. The regolith is composed of materials ranging from fine dust to small rock fragments. Its composition primarily includes minerals such as plagioclase feldspar, pyroxenes, and olivine. Rare minerals have also been detected within the regolith layer. The depth and thickness of the regolith vary depending on the region and geological structures of the Moon. In some areas, the regolith is only a few meters thick, while in others, it can reach depths of tens of meters. The depth is influenced by factors such as the number of meteor impacts, volcanic activity, erosion, and the effects of gravity. The regolith layer is densely packed due to the influence of lunar gravity, making walking or driving on the Moon a different experience compared to Earth. With gravity on the Moon being about 1/6 of that on Earth, less resistance is felt when moving across the regolith. The regolith layer on the Moon acts as an insulating layer against surface temperature fluctuations. The temperature differences between the long lunar day and night periods are extreme. During the day, the Moon's surface can become very hot, reaching up to 100 degrees Celsius, while at night it can drop to extremely cold temperatures, as low as -150 degrees Celsius. The regolith serves as a buffer against these temperature changes, helping to moderate the heat transfer to the deeper layers of rock beneath the surface. Research into the regolith layer is essential for understanding the Moon's geological evolution, crater formation, volcanism, the effects of meteor impacts, and its resource potential. The Apollo missions and other space explorations have collected samples of regolith and brought them back to Earth. These samples have provided critical information about the Moon's geological history and the evolution of the solar system. Additionally, lunar exploration vehicles have conducted detailed analyses of the regolith, measuring its physical and chemical properties. These studies have offered valuable insights into the Moon's resource potential, including the presence of water molecules, element distribution, and radioactive characteristics. The findings contribute crucial data for future lunar exploration and colonization efforts. The regolith layer has deepened our understanding of the Moon's geological structure and formation processes. Scientists plan to conduct further research through future space missions and exploration projects to gain more knowledge about the regolith. These efforts will help reveal more about the Moon's geological history, its resource potential, and its strategic importance as a base for space exploration. For a long time, the amount of water on the Moon was a topic of debate, with the prevailing belief being that the Moon was a dry, barren body. However, recent studies and discoveries have confirmed the presence and quantity of water on the Moon. Initially, it was thought that water on the Moon existed only in isolated pockets of ice, but further research has shown that water molecules are more widespread across the lunar surface. There are two primary sources of water on the Moon. The first is found in the form of ice in extremely cold, shadowed regions known as supercold traps. In these areas, which are shielded from sunlight and remain sufficiently cold, water molecules can be preserved in the form of ice. The second source is known as bound water, which exists within the rocky layers of the Moon. These water molecules are trapped within the crystalline structure of the rocks. Research and discoveries. Several spacecraft and missions have been employed to detect and analyze the amount of water on the Moon. Missions like Chandrayaan-1 sent by the Indian Space Research Organization, Lunar Reconnaissance Orbiter, and Lunar Crater Observation and Sensing Satellite have provided significant data on the presence and distribution of lunar water. Chandrayaan-1 confirmed the existence of water molecules on the Moon by analyzing the sunlight reflected from the surface. The LCROSS mission impacted a crater near the Moon's south pole, ejecting material that was later analyzed to confirm the presence of water vapor and ice. Meanwhile, the LRO mission conducted more detailed studies on the Moon's surface, mapping the distribution of water molecules across different regions. Although the exact amount of water on the Moon has yet to be fully determined, research indicates that millions of tons of water are present in the form of inflamed water trapped within the lunar soil. These water molecules are bound within the regolith layer and are more widely distributed across the Moon's surface than previously thought. Research has also revealed the presence of concentrated water ice in the Moon's dark and cold craters. In these craters, which are shielded from sunlight, water molecules can remain in the form of ice in supercold traps, offering significant potential as a resource for future space missions. Determining the exact amount of water on the Moon and mapping its distribution in greater detail is crucial for future lunar exploration and colonization projects. Lunar water sources could be considered a potential fuel source through the process of water splitting to obtain oxygen and hydrogen. Additionally, the oxygen produced from water splitting could be used in life support systems for human presence on the Moon. We have learned some information about the Moon's surface. So, what are the physical characteristics of the Moon? The Moon's diameter is approximately 3,474 kilometers with a radius of about 1,737 kilometers. This is roughly 1/4 of Earth's diameter. The Moon's surface area is about 37.9 million square kilometers. Compared to other moons in the solar system, the Moon is quite large. For example, Phobos, the largest moon of Mars, has a diameter of only about 22 kilometers, while Ganymede, Jupiter's largest moon, has a diameter of approximately 5,268 kilometers. Therefore, the Moon is considerably larger compared to other moons. The Moon's mass is approximately 7.35 times 10 to the power of 22 kilograms, which is about 1.2% of Earth's mass. The Moon's mass is relatively small compared to other bodies in the solar system. For instance, Jupiter's mass is about 1.9 times 10 to the power of 27 kilograms, and the Sun's mass is roughly 1.98 times 10 to the power of 30 kilograms. Thus, the Moon has a smaller mass compared to these larger bodies. The chemical properties of the Moon's surface are determined by its composition and mineralogy. A large portion of the Moon's surface is covered by silicate minerals, including feldspars, pyroxenes, olivines, and amphiboles. These silicate minerals play a crucial role in the formation of the Moon's dark plains, known as Maria, and its mountains. The Moon's surface is rich in compounds containing the element oxygen. A significant amount of the Moon's oxygen is found in the form of oxides. Compounds such as iron oxide and titanium oxide are particularly common on the Moon's surface. The presence of hydrogen on the Moon's surface has been observed. Much of the hydrogen exists in the form of water molecules. Concentrated water ice has been discovered in the Moon's dark and cold craters. Additionally, it is believed that hydrogen may also be present within the structure of rocks. Metallic elements are also found on the Moon's surface. Elements such as iron, aluminum, calcium, magnesium, and titanium are commonly found in the Moon's surface compounds. The density of the Moon is calculated by considering its mass and volume. The Moon's density is approximately 3.34 grams/cm superscript 3, which is about 60% of Earth's density. Earth's density is approximately 5.52 grams/cm superscript 3. Variations in density may be attributed to differences in the Moon's internal structure. It is likely that the Moon's crust, mantle, and core contain materials of varying densities. For example, the Moon's crust is thought to have a lower density compared to other layers. These differences can provide insights into the Moon's formation and geological evolution. The gravitational force on the Moon is a result of its gravitational field and causes objects to be attracted toward the Moon. This gravitational force varies depending on the Moon's mass and size. The Moon's gravitational field is weaker compared to Earth's because the Moon is smaller in mass and size. Gravitational force acts on objects on the Moon's surface. The strength of the Moon's gravitational field is measured by gravitational acceleration. The gravitational acceleration on the Moon is approximately 1.622 meters per square second, which is about 1/6 of Earth's gravitational acceleration. This means that objects fall more slowly on the Moon compared to Earth. The gravitational force on the Moon affects the movement of objects. An object on the moon's surface is pulled toward the moon due to this gravitational force. As a result, objects weigh less on the moon than they do on Earth. For example, a person's weight on the moon is roughly 1/6 of their weight on Earth. The gravitational force on the moon also influences movement on its surface. The moon's lower gravity allows people to jump higher and makes it easier for vehicles to move compared to Earth. The gravitational force affects living conditions on the moon as well. The moon's low gravity influences the flow of liquids, resulting in lower surface tension of water. Additionally, the moon's gravitational force can impact important factors like the formation and retention of an atmosphere. The moon's magnetic field is related to its internal structure and geophysical properties. Compared to Earth's magnetic field, the moon's magnetic field is quite weak. The moon does not have the ability to generate a natural magnetic field. However, the moon's magnetic field is influenced by Earth's magnetic field. The moon's magnetic field is generated by the interaction of charged particles carried by the solar wind that reach the moon's surface, influenced by Earth's magnetic field. When these particles collide with the moon's surface, they create a magnetic effect, which forms the moon's magnetic field. The moon's magnetic field differs from Earth's. While Earth's magnetic field behaves like a magnetic dipole, the moon's magnetic field has a more complex structure. The moon's magnetic field can be affected by the magnetic properties of minerals and rocks within its interior. The moon's magnetic field has been measured by moon missions and space explorations. Magnetometers placed on the moon during the Apollo missions were used to measure the moon's magnetic field. The data obtained indicated that the moon's magnetic field is quite weak and is influenced by Earth's magnetic field. The moon's magnetic field provides information about its geological evolution and internal structure. Magnetic field data can offer clues about the magnetic properties of minerals and rocks on the moon. This information helps in gaining a better understanding of the moon's formation and geological processes. The moon is a celestial body without an atmosphere. Therefore, instead of discussing an atmosphere, we can talk about the thin layers of gas and dust on the moon's surface. The moon has a very thin layer of gas with extremely low density. This layer consists of gases and particles that are carried by the solar wind and impact the moon's surface. However, this gas layer cannot be considered a traditional atmosphere due to its extremely low density and lack of atmospheric functions. The gas layer on the moon's surface primarily contains noble gases. These noble gases, such as helium, neon, and argon, are elements that have been ejected from the moon's surface and become gaseous due to the effects of the solar wind. Despite their presence, these gases have such low density that they do not constitute an atmospheric layer. Additionally, there are fine layers of dust and particles on the moon's surface. These dust and particles result from impacts on the moon's surface and remain there due to gravity. The dust and particles cover the surface and give the moon its characteristic gray color. Although they are not dense enough to be considered an atmosphere, they affect the optical properties of the surface and influence the moon's appearance. The formation of the moon is generally accepted among scientists as being based on the giant impact theory. According to this theory, about 4.5 billion years ago, during the early stages of the solar system, the moon was formed as a result of a collision between the young Earth and a planet-sized object approximately the size of Mars. This collision occurred when a planet called Theia struck the Earth. As a result of the collision, a large portion of Theia was fragmented, and these fragments gradually coalesced to form the moon. The materials from both Theia and Earth mixed together, resulting in a moon composition that is quite similar to that of Earth. This collision initiated the moon's formation process, and it eventually became Earth's satellite by orbiting around it. During the formation of the moon, some of the energy and heat released from the collision caused the moon to melt. The resulting molten lava spread across the moon's surface, initiating the volcanic activity of the young moon. This lava created basaltic layers that covered the moon's surface. With the formation of the moon, the intense bombardment period of the early solar system also began. Asteroids and comets continually impacted the moon's surface, resulting in craters and depressions that have become characteristic features of the moon. Captured by Earth's gravitational pull, the moon started to orbit around Earth. This orbital movement caused the same side of the moon to always face Earth, a phenomenon known as tidal locking or synchronous rotation. The formation of the moon provides valuable insights into the evolution of the solar system and the planetary formation process. By studying the geological features of the moon, scientists gain a better understanding of the early stages of the solar system and the formation of Earth. The moon orbits Earth in a circular orbit determined by Earth's gravitational influence. The moon revolves around Earth as its satellite. The moon's orbit is influenced by Earth's gravitational force, which is a result of Earth's large mass and strong gravitational pull. This force attracts the moon towards Earth and keeps it in orbit around our planet. The moon travels along an elliptical orbit around Earth. This elliptical path causes variations in the moon's distance from Earth and its speed. The moon moves between 2 points called perigee and apogee. Perigee is the closest point to Earth, while apogee is the farthest point from Earth. The moon's orbit is controlled by Earth's gravity, making the moon behave like a falling object under Earth's gravitational influence. Consequently, the moon experiences an acceleration towards Earth. However, the moon's orbital speed and the gravitational effect create a balance that prevents the moon from continuously falling towards Earth, allowing it to maintain its orbit. The moon completes its orbit in approximately 27.3 days, which allows it to make a full revolution around Earth. The moon's speed varies depending on its distance from Earth. It moves faster when it is closer to Earth at perigee and slower when it is farther away at apogee. The moon's orbit can also be influenced by the gravitational forces of other planets and the Sun. These influences can cause slight changes in the moon's orbit over time. This phenomenon is observed at points known as the moon's nodes, where changes in the moon's orbital inclination and plane are noted. Now, let's examine tides. Tides are the regular and repeating rise and fall of sea levels. They are caused by the gravitational forces and the interactions between the moon and the sun. These gravitational interactions affect Earth's fluids, creating tidal phenomena in the oceans and some lakes. The moon's influence is the most significant factor in tidal formation. The moon's gravitational pull creates a tidal force on Earth. As the moon orbits Earth, Earth's gravity pulls the moon towards itself, while the moon's gravity affects Earth's water bodies. The moon's gravitational force pulls the water masses near Earth, causing them to move towards Earth and resulting in a rise in sea level. This rise is known as the high tide phase, during which high tides occur. Simultaneously, on the opposite side of Earth, there is a point where the moon's gravitational force is less felt, causing the sea level to fall and low tides to occur. Tides interact with both the moon's rotation and Earth's rotation. The tilt of Earth's rotational axis influences tidal events, leading to the formation of tides with varying magnitudes and cycles. While the sun also contributes to tides, the effect of the moon is much more pronounced because the moon is closer to Earth than the sun. Tides have significant impacts on various areas, including marine life, coastal erosion, ship navigation, and maritime activities. In some regions, high and low tides create substantial differences in sea level, which can affect navigation and other maritime activities. An eclipse occurs when the sun, Earth, and moon align. Since the moon orbits Earth at a relatively close distance, it can enter Earth's shadow. However, not every new moon or full moon results in an eclipse. Because the moon's orbit is slightly tilted relative to Earth's orbit, the moon usually passes above or below Earth's shadow. An eclipse encompasses the rare instances when the moon enters Earth's shadow. There are two main types of lunar eclipses: total lunar eclipse and partial lunar eclipse. A total lunar eclipse occurs when the moon is entirely covered by Earth's shadow. In this situation, sunlight is refracted through Earth's atmosphere, casting a reddish hue on the moon. As a result, the moon often appears red during a total lunar eclipse. A partial lunar eclipse occurs when only a portion of the moon is covered by Earth's shadow. In this case, part of the moon remains in darkness while the other part remains illuminated. Partial lunar eclipses happen when the moon passes through only a part of Earth's shadow. Lunar eclipses are typically observed during the night. Since the moon is positioned directly opposite the sun, lunar eclipses usually occur during a full moon. Eclipses can be observed worldwide, but it's important for the observation location to be close to midnight for the best viewing. A lunar eclipse presents an exciting observation opportunity for astronomy enthusiasts. People can observe this event using telescopes or with the naked eye. Lunar eclipses are also important for scientific research. Spacecraft studying the moon can collect data on the moon's atmosphere and surface during an eclipse. Lunar eclipses hold significant historical and cultural importance as well. Many cultures have incorporated lunar eclipses into their mythological and religious narratives. Historically, lunar eclipses have helped people develop their understanding and tracking of natural phenomena. Scientifically, lunar eclipses help us understand the movements of planets, moons, and the sun. They aid in our comprehension of fundamental astronomical principles and expand our knowledge of how the universe functions. Additionally, lunar eclipses allow us to better understand the gravitational interactions between the Sun, Earth, and Moon, and the dynamics within the solar system. Observations of the Moon have been recorded by humans throughout history. Tracking and observing the Moon's movements has been a consistent endeavor since the earliest periods when people sought to understand natural phenomena. In ancient times, the Moon was a source of great curiosity and admiration for humans. Observing and attempting to understand the Moon's movements stemmed from the need to monitor natural events and organize their calendars. The Egyptians meticulously tracked the Moon's movements. For them, the Moon symbolized fertility and time. By observing the Moon's phases, they planned their agricultural activities and used its movements to predict the flooding of the Nile River. The Babylonian civilization systematically recorded the Moon's movements and created lunar calendars. Babylonian astronomers carefully observed the Moon's phases and eclipses in an attempt to forecast future events. They also used the Moon's movements to determine the positions of other planets. The ancient Greeks also observed the Moon's movements and studied them mathematically. They developed geometric models to predict the Moon's rotation speed and orbit. The Moon's movements were a significant area of interest in both astronomy and mathematics. During the Roman Empire, observations of the Moon's movements and phases continued. The Roman calendar system was based on the Moon's phases and was organized into lunar months. Tracking the Moon's movements was crucial for scheduling agricultural activities and planning religious festivals. In the Middle Ages, observations of the Moon played an important role in scientific studies and interest in astronomy, particularly in Europe. Scientists in the Islamic world also studied the Moon's movements and made significant contributions to the field of astronomy. During the Middle Ages, scientists in the Islamic world carefully observed the Moon's movements and phases. Islamic astronomers used observations and mathematical calculations to predict the Moon's orbit and phases. Notably, scientists such as Ibn al-Haytham, al-Hazan, and Nasir al-Din al-Tusi made significant contributions to the study of the Moon's movements and eclipses. In Europe, although scientific work was limited under the influence of the Church during the Middle Ages, observations of the Moon were still conducted by many scientists and astronomers. Monks, in particular, observed the Moon's movements and kept detailed records. These observations were used to create lunar calendars and perform calendrical calculations. In the Middle Ages, moon observations were generally based on visual tracking and mathematical calculations. Observing the Moon's movements was crucial for keeping time, organizing calendars, and performing astrological calculations. Observations of the Moon's phases and movements contributed to scientific studies and the development of astronomical knowledge. However, during the Middle Ages, there were some limitations to scientific progress and observational work. The influence of the Church and dogmatic thinking constrained observational and astronomical studies. In the early modern period, moon observations gained significant momentum with the advancement of technology and an increase in scientific research. Observations of the Moon during this time became more comprehensive, incorporating both telescopic observations and manned lunar missions. The invention of the telescope in the 17th century brought a new dimension to moon observations. In 1609, Galileo Galilei used a telescope to examine the Moon's surface in detail. Galileo's observations allowed him to discover the Moon's mountains, craters, and seas. Following his work, other astronomers and amateur observers used telescopes to study the moon and gather new information. In the 1960s, the Apollo program elevated moon observations to an entirely new level with manned lunar missions. Apollo astronauts landed on the moon, conducted close-up examinations of its surface, collected samples, and gathered scientific data. These missions provided comprehensive information about the moon's geology, craters, rocks, and other physical features. In the early modern period, space telescopes and orbital instruments also played a significant role in moon observations. Telescopes like the Hubble Space Telescope have been used to study the moon's surface and features in greater detail. Additionally, spacecraft in lunar orbit have been employed to measure and examine the moon's magnetic field, gravity, and other physical properties. Today, both amateur astronomers and professional scientists continue to observe the moon. Telescopes, cameras, and other observational tools are used to study the moon's surface, craters, mountains, and other details. Space agencies and astronomy communities are also engaged in research and projects related to moon observations and exploration. For instance, NASA's Artemis program aims to return humans to the moon and observe it in greater detail. These observations will provide further insights into the moon's geology, volcanism, resources, and potential signs of life. Moon observations are conducted not only for scientific discovery but also for educational purposes, cultural heritage, and public interest. Events such as lunar eclipses are significant astronomical events that attract wide public attention. Amateur astronomers and enthusiasts organize various activities to track, photograph, and observe the moon. Don't forget to subscribe for new documentaries and more scientific content.